So in this lecture, we will introduce the linear models in time series. As I said, we will be talking mostly in mathematical terms because kind of whenever you are modeling, you need to know what kind of model you are trying to build. And every model has its own characteristics, and we need to understand these characteristics. Well, what we have covered in the previous lecture, a time series is a sequence of random variables that is ordered in time. And the problem is in time series is that the observations are usually dependent. Our goal, practical goal, is to model this dependence relationship. We know that the most fundamental thing in time series is stationarity. Without stationarity, you are in such troubles as whenever you have non-ID samples in cross-sectional econometrics. When we talk about strict stationarity, it requires that the joint distribution of a sequence of variables is invariant under time shift. This is a very strong assumption because it is not testable. Basically, you are not able to verify if the joint distribution is the same or not. But less strict and more practical requirement is the weak stationarity. In the weak stationarity, well, the kind of requirements for the weak stationarity are simple. The mean doesn't change over time, so any t that you take, t1, t2, t3, t330, the expected value of y is the same. The variance is finite, doesn't change over time, and the autocovariance is finite, doesn't change over time, and depends on h. So it depends on the lag between t and the moment in the past, kind of t minus h. So we will start talking about linear time series, and we will introduce several classes of models. So they are following here: autoregressive models, moving average models, and after regression moving average models. So they're a combination. So we will start with the definition of what are the linear time series. Of course, I'm not covering everything about time series here because, well, the most fundamental books in time series are kind of like 1000 pages. And as I said, this is the separate large topic, how to work with time series and all these details and properties and blah, blah, blah. So we are just talking about the most important things for you to understand in the future how to work with time series and where to go if you need to get some additional knowledge. So we introduced the first type of linear time series, which is called the white noise, similar to physics. A time series is called a white noise when this is a sequence of independent and identically distributed random variables with expected value 0 and variance sigma squared. So white noise is something similar to IID error term in cross-sectional econometrics. So we usually denote white noise with epsilons, and given that this white noise is IID, so covariance between t and s is gonna be 0. Well, because this is independent and identically distributed random variables. If they are independent, covariance is 0. So independency implies 0 covariance. Yes, as I said, the white noise is an analog of IID random variable in cross-sectional econometrics. So we need to introduce similar thing in order to work with this. Now, a linear time series is when it is, well, it must be YT, of course. So a linear time series YT is such time series that can be written as the sum of this white noise series multiplied by coefficients psi plus some constant. So this is the definition of linear time series. Whenever you are able to represent your series in such form, you can be sure that the series are linear. Mu is the mean of yt. This is, I guess, obvious, because expected value of this sum is 0, given that expected value of every epsilon is 0. Expected value of constant is constant, right? So expected value of mu yt is mu. So psi 0 is 1 always, and epsilon t is a white noise. So these psi t's are called the psi weights of yt. And the structure of yt is kind of governed, is constructed with these psi weights. So now, what are the problems? So this is a general definition of linear time series. Again, any series that can be represented with this form is linear. So we are not gonna provide some proofs that this is not linear time series. We will take as given, kind of, you can believe me, that the series that we are gonna cover today, all of them are represented in this form and all of them are linear. So what are the properties of linear time series? First of all, mu is the expected value of yt. Variance of yt depends on that sum of psi's and epsilons. And basically the variance of yt, given that epsilons are white noise and they are IID and they have some variance, sigma squared epsilon. So variance of yt is just this sigma multiplied by the sum of squared weights, of squared psi's. So autocovariance function for linear time series can be built in the following form. So this is the covariance between yt and yt minus h here. So we kind of drop mu for a while. Mu doesn't really matter here. So then this sum, when we do the cross product, it is represented as this. And then finally, so expectation of the sum is the sum of expectations. So we have this. And given that expectation of epsilon squared is gonna be sigma squared, so we have something similar to the variance. This is sigma squared of epsilon multiplied by the sum of cross products of the psi's of these coefficients. So basically you need to take the coefficient from j to infinity and j plus h to infinity and multiply them and sum over them. And now related to the autoregression function, if you take this autocovariance, if you take this variance, and if you divide them like this, what do we have? We have sigmas cancelled out, and we have finally this form. Again, because psi 0 in the bottom, in the denominator is 1, so we kind of take this out of the sum. So we see that j here, and now it is I from 1. So j was from 0, I starts from 1, because psi 0, as was given here, psi 0 is 1. Well, when we build linear time series, those are econometric models that we use to describe the pattern of psi weights of yt. So basically you see that why are we talking about linear models? Why do we want to introduce this white noise concept? Because in this case, everything all the properties, all the characteristics of the series depend on psi's, and depending on the psi's, on their values, covariance, autocorrelation, and variances are changing. So this was a general introduction of linear time series, the most general way of talking about time series. Now we go closer to the practice. We will take three classes of models: AR models, autoregressive, moving average MA models, and their combination ARMA models. And we will talk about their properties. So when they are appropriate for modeling time series, when they are not appropriate for modeling time series, and well, how to characterize them. So first of all, the simplest case of autoregressive models is the first order autoregressive model, AR1. This is the definition of this model. So yt equals to phi 0 plus phi 1 multiplied by yt minus 1. So the previous value of y affects through phi 1 affects the current value of yt. Additionally, there is some constant term and some noise, the unexpected change in the variable. So as you see, white noise here plays the same role as the error term in cross-sectional econometrics. So if we assume that AR1 series is weakly stationary, so for now we don't know, but let's assume that this is stationary, so expected value of yt is mu. Variance of yt is, so these are just some kind of notations. Now, what are they related to the parameters of the model? So let's talk about the properties of AR1 model, and this is what you need to do in the exercise sessions, and also this is what you can expect from the home assignment. So please be careful here, because now we are starting to talk about some practical applications of this series. So how to construct the mean of AR1 process? Expected value of yt is the expected value of this expression. Now, expected value of the sum is the sum of expected values. Expected value of phi 0 is phi 0. Expected value of y1 times yt minus 1 is phi 1 times the expected value of yt minus 1. Expected value of epsilon is 0 here. So if we assume stationarity, only if we assume stationarity, then expected value of yt equals to the expected value of yt minus 1. So, and they equal to mu. So we can kind of change the notation. So mu equals phi 0 plus phi 1 mu. So finally, expected value of yt, which is mu, equals to this, phi 0 over 1 minus phi 1 here. There are two implications from this. First of all, what do we see here? Phi 1 cannot be equal to 1. So this coefficient should not be 1. Otherwise, the mean does not exist. And the mean of yt is 0 if and only if phi 0 is 0. Right? So if phi 0 is 0, then yt, mean of yt is 0. So the first implication is the very important thing. So we are gonna talk about this later. But this is very important thing. Now, regarding the variance. So variance of yt, again, we plug into the variance operator the expression. So the variance of constant is 0. Variance of this part is phi1 squared times the variance of yt minus 1, plus variance of white noise is sigma squared of the white noise. Yeah, epsilon t and yt minus 1 are independent, of course. So normally, the observation yesterday does not depend on the random outcome today. So logically, they are independent. Again, if we assume the stationarity, then these variances are equal. And so we just plug here variance of yt. Again, this comes from our assumption that the process is stationary. So we plug everything there, and finally we derive what is the variance. So variance is sigma squared of epsilon over 1 minus phi1 squared. What else do we see here about phi1? So the variance of yt exists only if phi1 is bounded between minus 1 and 1. So this is additional implication on phi1. Phi1 should not be 0, phi1 should not be 1, and phi1 should be bounded between, oh wait, phi1 can be 0. But if phi1 is 0, this is redundant, right? Because, yeah, sorry. Phi1 cannot be 1, and phi1 should be bounded between minus 1 and 1, not included. Because otherwise, what happens? Otherwise, variance is going to be negative, which is forbidden. So negative variance is a nonsense. Variance should be positive. So, again, regarding the properties, so what are the conditions of stationarity of AR1 model? So now we assumed that this is stationary. But assuming that this is stationary, we constructed the properties of this series. And after the construction of these properties, we can impose some restrictions. If phi1 is not 1, and if phi1 is bounded between minus 1 and 1, then this is a necessary and sufficient condition for AR1 model to be weakly stationary. So the absolute value of phi1 should be less than 1. If this coefficient in absolute value less than 1, then the whole model is stationary. And if the model is stationary, then, well, it has a good properties for us, let's say, for now. Good and pleasant properties. So now, we spoke something about linear models before in general form. Was here, right? So here. So now, we introduce something new, AR1 model. Are these two things related somehow? Let's see. So let's take that there is AR1 model with mu equals to this. So if we rewrite phi0 to be mu times 1 minus phi1 and plug into the model, we get this. So then we subtract mu from both sides. And we have this. Then we substitute for the previous period yt minus 1 minus mu, which is phi1 times yt minus 2 minus mu, into the formula. We get the following thing. So we take this and we kind of recursively write down what is yt minus 1 minus mu according to the following rule. So this is phi1 squared times yt minus 2 minus mu plus phi1 times epsilon t minus 1 plus epsilon t. So we keep doing this again and again. So if we plug here yt minus 2 as phi1 times yt minus 3, minus mu plus epsilon t minus 2, we will get the following sequence finally. Epsilon t plus phi y epsilon t minus 1 plus phi 1 squared epsilon t minus 2 that appears here plus ta 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 ta. So finally we have this. Finally we have the sum of infinite sum of phi's 1 to the power of I times epsilon t minus 1 I, which is what? So this difference, again, sorry for the typo, this must be yt minus mu, so is a linear function of epsilons. Therefore, AR1 model is the linear model. Now, for AR1 model, we know what is mean, we know what is variance. What else should we know? In the first lecture, we said that for any time series, we want to know mean, variance, covariance, and autoregressive, autocorrelation function. So let's build them. What is the autocovariance function here? Again, we start with the following representation, so demeaned representation of yt, so yt minus mu here, yt minus 1 minus mu here. So we multiply both sides by epsilon and take expectation, like this. So what is the trick here? The trick here that on the left hand side, expectation of this part is 0. So epsilon t is not correlated with the past observation. So this expectation is 0. This expectation is just epsilon t squared, which is variance of epsilon, sigma squared epsilon. So now we multiply the initial expression by yt minus h minus mu and take expectations. So here, so when we multiply the left hand side, we get exactly the autocovariance function or autocovariance expression. On the right hand side, we have this phi 1 times yt minus 1 minus mu plus epsilon t multiplied by yt minus h minus mu, right here. But the expectation of yt minus h minus mu times epsilon t is 0, right? This part is going to be 0. So now we have two cases, basically. If h is 0, this expectation is non-zero. Sorry, I was kind of too fast. If h is 0, this expectation is not 0, and this expectation is just the autocovariance of order 1. If h is larger than 0, then this second term disappears, it's 0. And we have this. We have phi 1 times gamma h minus 1. So this is autocovariance function. We constructed the autocovariance function. So autocovariance for h0, which is variance, equals to this. Autocovariance of any order larger than 0, 1, 2, 3, 4, 5, equals to this. So autocovariance is itself depends on the previous values. Now, autocorrelation function. So let's list what we know. Variance of yt is here, covariance of yt is here for h larger than 0. So now, what is the autocorrelation function? We take the covariance, divide by the variance. And variance is here. And what is this fraction? Gamma h minus 1, gamma 0. This is autocorrelation between h minus 1 lag and 0's lag. So basically rho h depends on rho h minus 1 multiplied by phi 1. And because rho 0 is 1, we have ph, which is equal to this, just phi 1 to the power of h. Rho h, sorry. So the autocovariance function of a weakly stationary AR1 series decays exponentially with rate phi1. It starts at row 1, row 0 equals 1, and then it goes down. Something like this. So if you take the following AR1 process with phi 0.8, so we start at 1, then the next value of autocorrelation is 0.8, the next is 0.64, the next is whatever, 0.64 times 0.8, and so on. It goes down, 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 never reaching 0, of course, but going very close to 0. If there is minus 0.8 coefficient in front of yt minus 1, then it kind of jumps to the negative and positive areas, right? So it starts from 1, then it's minus 0.8 here, then 0.64 here, then minus something here, and so on. So it jumps like this. So whenever in the data you see such pattern of autocorrelation function, you can immediately suggest that this is AR1 model, AR1 process. Or AR1 process is suitable for modeling the data. Now, moving average models. What is this? Well, moving average model of order 1 has the following structure. So this is YT, which consists of 3 parts: mu, mean, epsilon t, the white noise at the current moment, minus theta 1 times epsilon t minus 1. So white noise in the previous period. Again, epsilon t is a white noise. MA models are always weakly stationary, so there are no conditions on the stationarity as we had in AR1 process when phi 1 should be less than 1 in absolute value. Oops. And MA model always have a linear model representation because it is already a linear model representation, right? So this is the sum of epsilons. So expected value of yt is mu. Variance of yt is this. So we have it here. No, but let's inspect what is how to build this variance. So this is very simple. You just can imagine this. The only relevant part is this. So variance of white noise minus theta 1 times white noise. So what is variance? So they are independent because this is white noise and white noise is IID. So which means that there is no correlation here. Now, since there is no correlation here, the variance of this, so the variance of constant is 0, right? So we don't care about this. We care only about all these two terms. What is variance of epsilon t? This is sigma, right? What is variance of this theta 1 epsilon t? This is theta 1 squared times sigma. So now sigma goes out of the bracket and we have this 1 plus theta 1 squared. So this is even easy to imagine kind of without any derivations and computations. So now, how the autocovariance function of MA model looks like. We do the same trick. We subtract from both sides mu, and then we multiply both sides by yt minus h minus mu, and take expectations. This, and this is the right-hand side. Epsilon t times yt minus h minus mu minus theta 1 epsilon t minus 1 multiplied by this. Again, we have two cases here. If h is 1, then this part becomes this theta 1 with minus sigma squared epsilon. Why? Because, well, we just plug here yt minus 1 in the following form, and we get epsilon t minus 1 and epsilon t minus 1. So when h equals 1, we have this. Whenever h is greater than 1, there is autocovariance, which is 0, because this is 0, and this is also going to be 0. No relationship at all. And regarding the autocorrelation function, we know what is variance, we know what is covariance, we know that this covariance is 0 for any h which is greater than 1. So the autocorrelation function is this. We take covariance, divide it by variance, sigmas cancel other, and we have minus theta 1 over 1 plus theta 1 squared for the first order, for the first log. All the other logs are 0. For h larger than 1, rho h is 0. So when you inspect ACF for MA1 model, there is only one column at log 1, which is here, and then it disappears. So these models are called sometimes finite memory models. So your model forgets what has happened, let's say 2 periods before. Because there is no autoregression and autocorrelation between them. Well, and now we combine both classes of models in the following way. So ARMA 1.1 model can be constructed as yt equals to phi 0 plus phi 1 yt minus 1 plus the moving average part epsilon t minus theta 1 epsilon t minus 1. So no idea why there are no minuses. Again, some bug here probably. So it must be t minus 1 here and t minus 1 here. So first of all, in order for have a meaningful model, phi 1 should not be equal to theta 1. Otherwise, it is going to be not ARMA 1.1 model. So regarding the mean of this model, if we move phi 1 yt minus 1 to the left and take an expectation, and remember that this is a stationary process, so expected value of yt and expected value of yt minus 1 are equal, so they equal to mu, and these are zeros. So we see that expected value is the same as for AR1 model. And variance with no derivation looks, well, not horrible yet, but unpleasant, let's say, because there are some interactions between phi's and thetas, and if we have larger order model like 2 or 3 order for autoregression, this variance is going to be a nightmare. And ACF and also autocorrelation function for ARMA model looks, well, for the first lag it looks unpleasant. For the second lag it's just the same as for AR1 model. So there is autoregression through the coefficient phi 1. And again, stationarity condition for this model is the same. So the absolute value of phi 1 should be less than 1. Well, we went through 3 classes of linear time series models that have different characteristics. So now your future is going to be to work more with the kind of exact examples of such variable of such series. This is what you are going to do in the exercise sessions. And you will try to derive again this mean, variance, and covariance of the series. So each model can be uniquely characterized by the autocorrelation function. So basically, the structure of autocorrelations is different for different models. And we work with the real data. The first step is to identify the appropriate model that fits the data. And this identification is going to be based, so how to identify, this is what we are going to talk about in the next lecture. We will start the practical application of everything that we have discussed today to the real data. So your plans for the future. Quiz number 5 is going to be based on these lectures, on the today's lecture, 9 and 10. Gonna be available till the next, what is that? Till the next Friday midnight. On Friday, you have the exercise session. This exercise session is going to be about time series and linear time series and the properties of linear time series. And the home assignment number 6, available till November 23rd, so 2 weeks ahead here, is going to be based on the simple derivations for AR, MA, and ARMA models, based on what we have done today. So you will be given some exact AR model with exact coefficients, and the question is going to be compute mean of this process, or compute variance of this process, something like this. So simple computations just to somehow move you back to mathematics, and in order to somehow motivate you to start thinking not in the terms of estimation only, but also before estimating some model, you need to understand what are the properties of the model that you estimate. Any questions, friends?